Today we're going to take a look at how to graph a function pretty much perfectly without having to use our graphing calculator. So in order to do this, we're going to have to find a lot of different things. First, we're going to have to find x and y intercepts, and then we're going to use our derivative to find maximum and minimum, both local and absolute, as that applies. We'll also use a second derivative to find points of inflection. We'll look for asymptotes using limits, and we're going to determine all intervals on which the function might be increasing and decreasing, and where it's concave up and concave down. So to start with, we'll do everything that we might be able to do without taking a derivative first. So in order to see where this function has x and y intercepts, to find the y intercept, we just have to look at the constant term. For x to the fourth minus 4x cubed, the constant term is 0, which means this has a y intercept 0. And find the x-intercept, we'll just set the function equal to 0 and solve. We'll factor out an x cubed, leaving us with x minus 4. And that tells us that x is 0 and x is 4. So we know that we have x-intercepts 0, 0, and 4, 0. And I'll put those on here now. I'm going to make each square on the x-axis 1. And we have a y-intercept, as we said a second ago, of 0, 0. This is just a polynomial function, and we know that polynomial functions don't have any asymptotes, so we'll just say there are no asymptotes. It might be beneficial to think about what's going on as this function goes towards infinity and negative infinity. It's a fourth degree function, which means it's either going to look like this or like this, perhaps with some little local maximum or minima inside of it. But since it's got a positive a value, we know it's going to be going towards infinity, both on the right and the left-hand side. As x approaches infinity and as x approaches negative infinity. All right, so that's about all we can do here. The x and y intercepts and the asymptotes without taking a derivative. So now we'll take a derivative, and from our derivative, we'll be able to find maxima and minima and where the function increases and decreases. So our derivative is just 4x cubed minus 12x squared. And from there, we'll just set that equal to 0 and see when it's undefined. So first we'll set it equal to 0. We'll factor out a 4x squared, leaving us with x minus 3. And that'll give us x is equal to 0 and x is equal to 3. And we'll make a note that f prime is never undefined. So we can see that our only critical values are at x equals 0 and x equals 3, which means we'll put them on a sign chart, test values of f prime, to see if f is increasing or decreasing on each interval. So if I plug a negative value into 4x squared times x minus 3, let's say negative 100, 4x squared becomes a positive, and negative 100 minus 3 is a negative. And we can see overall that's negative, which means our function is decreasing from negative infinity to 0. Then we'll take a look at between 0 and 3. So if we plug in something between 0 and 3, like let's say 1, 4x squared is still positive, and 1 minus 3 is still negative, and we get negative. This function is still decreasing from 0 to 3, which means that our function does not have a local max or a local min at x equals 0. Then we'll test something greater than 3, like a million, and that makes 4 times a million squared positive, and a million minus 3 is positive. This interval is a positive value for the derivative, which means our function is increasing, giving us a local minimum at x equals 3. And of course, we'll need to figure out what that local minimum value is. So we'll find f of 3. If we plug 3 into that, 3 to the 4th power is 81. And then we're going to subtract from that 4 times 27, which is 108. We've got 81 minus 108, which ought to be negative 27. And clearly, if I make each square 1 on my graph here, I'm not going to be able to fit that on. Let's make each square here 3 going down. So 3, 6, 9, 12, 15, 18, 21, 24, negative 27 over here at 3. So this is the point 3, negative 27. And we've now got our maxima and minima. We just have a local minimum at 3, negative 27. And I think we should be able to see that that's actually going to be an absolute minimum, because our function is going to be decreasing from negative infinity all the way to 3. And then it's going to be increasing again after 3. So effectively, it's going to go down until we get to this point, and then back up after that point. So that's going to be our absolute and our local minimum. So I don't quite have the room to write that here, but we'll write it on the next page. And we don't have any absolute or local maximum. So we have a absolute and local min of negative 27 at x equals 3, and we'll say no local or absolute max. And then we know that this function was decreasing from our sign chart on the interval of negative infinity until we reach 3, which will include, because the College Board wants us to include endpoints on this. And then it was increasing after that from 3 to infinity. So the next thing that we need to do is find our second derivative so we can deal with the concavity. So f double prime of x should be, well, if we go back to what we had for f prime is 4x cubed minus 12x squared. So that derivative should become 12x squared minus 24x using the power rule. And we'll just need to set that equal to 0 and also see when it's undefined. We'll see that f double prime is never undefined, so we don't need to worry about that. But it does equal 0, and we'll factor this out. 12x times x minus 2 is equal to 0. And that gives us x equals 0 and x equals 2. And we'll throw those onto a sign chart for our second derivative to test for concavity on each interval and to see if we have a point of inflection at either of those values. So if I take a negative number, something to the left of 0, and plug it in, 12 times a negative is negative, and a negative number minus 2 is negative, which a negative times a negative gives us a positive, telling us on this interval from negative infinity to 0, our function is concave up. If we test something between 0 and 2, like 1, 12 times x, a positive number, but 1 minus 2 is negative, leaving us with a negative value, telling us our function is concave down between 0 and 2. And if we plug something more than 2 in, like a million, both 12x and x minus 2 end up being positive values. And our function switches back to being concave up, which means we have a point of inflection at x equals 0 and a point of inflection at x equals 2. We already know what f of 0 is, but we do need to find f of 2. If we plug 2 back into our original equation, the original equation was x to the 4 minus 4x cubed. That's going to be 2 to the 4th, which is 16, minus 4 times 8, which is 32. So that's just going to be negative 16. So we have points of inflection at 2, negative 16, and at 0, 0. And we can note that this is concave up on the interval negative infinity to 0, union 2 to infinity. And it's concave down according to our sign chart from 0 to 2, all non-inclusive on those intervals. So now we'll go back to our chart, or to our graph, and we'll plot the point 2, negative 16. So we'll go over to 2 and then down to negative 16, which should be just a little bit below right there. And we now have all the information we need to make this graph look perfect. We know that from negative infinity to 0, our graph is decreasing. And we also know that our graph is concave up on that, which means that it should look something like this. Then at x equals 0, we know that we have a point of inflection, which means our graph switches from 0 to 2 to be concave down. And on that interval, it continues to decrease. So we'll be concave down. And then at 2, our graph then has a second point of inflection at 2, negative 16, and flips to being concave up for the remainder of its domain. And we see that it's still decreasing from 2 to 3. So we'll continue decreasing, but concave up. Once it hits 3, it stays concave up and continues to be concave up for its entire domain. But then we start increasing until x goes to it. And we need to make sure as we go back up, we go through that x-intercept at 4, 0. And so we have now graphed this and checked off all the different things we needed to demonstrate. So we're going to do a couple more of these. This one's going to get, well, it looks like it's going to get a little bit more complicated, but it's really not going to be all that bad. We've got the cube root of x squared times 3 minus 2 times the cube root of x. We can start off here by not doing anything with the derivative and just looking for when this thing is equal to 0 and figuring out what the x and y intercepts are. So first, let's set f of x equal to 0. That means that the cube root of x squared would be 0, which just would be x equals 0, giving us an x-intercept of 0, 0, which conveniently means we don't need to look for a y-intercept. We've just found it. It's also 0, 0. And then we'll set 3 minus 2 times the cube root of x equal to 0, which would be 2 times the cube root of x equals 3. And then we'll divide by 2 and cube it, which gives us x equals 3 halves cubed, or 27 over 8. So we have a y-intercept of 0, 0. Check that off. We've got x-intercepts of 0, 0 and 27/8, 0. Check that off. And then we just need to plot that point at 27/8. I'm going to call each 2 lines here 1 now. So 2, 4, 5. And 27/8 is just a little bit over 3. It's 3 3/8. So 1, 2, 3, and just a little bit beyond 3, but not quite the 3½ yet. So somewhere right about there. We've already plotted the x-intercept of 0, 0, which is also y-intercept. And then we need to think about if this has any asymptotes. And we probably don't just know right away from looking at it, but we could look for a limit as x approaches infinity of f of x. And as x goes to infinity, well, we end up here in the cube root of x squared, that's infinite. And the cube root of x is infinite. But we have 3 minus 2 times the cube root of x, which makes the outside of the parentheses a positive infinity. and the inside of the parentheses a negative infinity, which means that this thing is going to go towards negative infinity. It doesn't have an asymptote, but we do know that as our graph goes towards infinity, it's going to be falling down towards negative infinity. And this will also help us determine that there is certainly not going to be any absolute minimum. And then if we look at a limit as x approaches negative infinity, when we plug that into what's outside the parentheses, we cube root x squared. When we square a very large negative, we get a very large positive. And then if we cube root that, we get another very large positive. So that's infinity. And then in the second part, when we cube root a very large negative, we get another very large negative. But then we multiply it by a -2, which makes it a very large positive. So this ends up being infinity times an infinity, which is infinity, which means that to the left, this thing is going to be rising up to infinity, which means that we're not going to have any absolute maxima either. So we don't have any asymptotes, so we'll make a note of that. I'll just write that over here. No asymptotes. And also no absolute maximum. And we'll write that in a minute once we deal with finding the derivative. So in the form that our function is currently, to find the derivative, we'd have to use the product rule. But if I wanted to make that a bit easier, I could just distribute this through, and then I will have to use the product rule. So f of x is also equivalent to, well, the cube root of x squared times 3. That's just 3x to the 2/3 power. So I'll write that. And then minus, when I do x to the 2/3 times x to the 1/3, that's just exponent rule. Add the exponents, 2/3 and a third is 1. So that's just going to be x. And then 1 is the coefficient down here, times a -2 is -2. So we'll end up with just -2x. And now that's in a much easier form to take a derivative of. So when I do that, I'll get f prime of x, and 3 times 2/3 using the power rule. That's just going to be 2. So 2x to the -1/3 minus 2. And this will be a little bit easier to visualize and deal with if we get rid of the negative exponent. Drop that to the denominator, 2 over the cube root of x minus 2. And we can stop there if we want, or we can get a common denominator. If we want to get a common denominator, we'll just do cube root of x. And we end up with f prime of x equals 2 minus 2 cube roots of x over the cube root of x. And we can see that this is equal to 0 if 2 minus 2 times the cube root of x equals 0. And that would tell us that 2 is equal to 2 cube roots of x, or 1 is the cube root of x, or x is 1. So there's one critical value. And this would be undefined if the cube root of x, the denominator, was equal to 0, which would be x equals 0. So we've got two different critical values here, x equals 0 and x equals 1. So we'll put those both on a sign chart and test some values on each interval in our derivative. So we'll start with a negative number. If I plug any negative number into a cube root, the result is still negative. And if I take a negative number and multiply it by -2 in that numerator, I get a positive. So 2 plus a positive is positive. And then in the denominator, the cube root of a negative is negative. So we have positive over negative. Positive over negative is always a negative, which means our function must be decreasing on that interval. If I plug in something between 0 and 1, we kind of have to be strategic about what we're going to plug in there. Something that's easy to cube root. So something that's easy to cube root between 0 and 1 would be like 1/8. That gives us 2 minus 2 times the cube root of 1/8. The cube root of 1/8 is a half. And then we'll divide that by a half. We can see that the numerator is just 2 minus 1, which is positive, divided by 1/2, which is positive. So this is positive, and our function increases from 0 to 1. And then something larger than 1, like 1,000,000, we could see that the cube root of 1,000,000 is still a pretty big number. If you multiply that by 2, it's even bigger. And if you do 2 minus something that's much bigger than 2, it's pretty obvious that we're going to get a negative value there. And then a cube root of a very large positive number in the denominator is positive, giving us overall negative, and our function decreases on that note. We don't need to evaluate the function at 0 because we already know it's equal to 0. But we do need to evaluate the function at 1. So let's find f of 1. It's 3 times 1 to the 2/3. And 1 to the 2/3 is just 1, so that's 3. Minus 2 times 1, that's just 2, gives us 1. So before we list out everything here, we'll go back to our graph and we'll plot a point at 1, 1. And we can see from our sign chart that we have a local minimum of 0 at x equals 0. And we have a local max of 1 at x equals 1. Neither of those are absolute extrema, as we said before, because of what the end behavior looks like. No absolute max or min. And our function is increasing only on the interval 0 to 1. And our function is decreasing from negative infinity to 0, according to our sign chart, union 1 to infinity. So that ought to give us a pretty good idea of what this looks like. Now we'll need to take a second derivative. Well, let's go back to the previous page where we had our derivative. We could take our fully simplified written out derivative here and take its derivative using the quotient rule. It seems a lot easier if we just went with this one that allows us to use the power rule. So the derivative of -2 is just 0. That constant goes away. And 2x to the negative 1/3 ought to be negative 2/3 x to the negative 4/3. Or negative 2 over 3x to the 4/3 power. This is never equal to 0 because the numerator would have to be 0. 2 doesn't ever equal 0, but it is undefined if 3x to the 4/3 equals 0, which just is x 0. Now, our function already has a local minimum at x equals 0, so we're definitely not going to have a point of inflection at x equals 0. But let's just show that that's true anyway by putting 0 on our sign chart and plugging in a positive and a negative number to our second derivative. So if I take a positive number and raise it to the 4/3 power, it will still be positive. And if I multiply that by 3 and then do -2 divided by that, I end up with a negative, telling me the function is concave down. And if I plug in a negative number to x to the 4/3, the cube root part of it keeps it negative. But when I raise it to the 4th power, it turns it into a positive. And with the -2 up there in the numerator, that's going to turn that all into a negative as well, telling us this function is concave down on its entire domain. So we would state that it's concave down from negative infinity to infinity. It is never concave up. And there are no points of inflection. Even though there was a place where the second derivative was undefined, there was no change in concavity at 0, thus no points of inflection. So we've now answered about maxima, minima, local and absolute, points of inflection, intervals when it's increasing and decreasing, and intervals when it's concave up and concave down. So now we just need to sketch it. And it doesn't look like we've got enough information here from just these 3 points, but really we do. We know that the function must be decreasing from negative infinity to 0, as well as concave down, because it was concave down on the entire interval. So here it is decreasing and concave down from negative infinity to 0. Our sign chart says that from 0 to 1, our function is increasing, but still concave down. And once it hits that local maximum of 1, it's going to then decrease from 1 to infinity. So we're going to increase from 0 to 1 and then decrease from 1 to infinity, but stay concave down on that whole interval. And we just got to make sure that we go through that other x-intercept. And there's our graph. This is the last one we're going to do today. We're going to look at f of x equals 2x times e to the x. So the first thing that we'll do is once again set our function equal to 0, which tells us that either 2x equals 0 or e to the x equals 0. That tells us that x is 0, and this is never true. So we seem to just have an x-intercept of 0, 0, which happens to also then be our y-intercept. So we'll just plot the point of the origin. And then we'll talk about asymptotes. So we've got our x and y-intercepts. Asymptotes can also be found without taking a derivative. So we'll find a limit as x approaches infinity of f of x. Well, 2 times infinity is infinity, and e to the infinity is infinity. So infinity times infinity is just infinity, which means that as this approaches infinity, as x approaches infinity, the function also goes to infinity. No asymptote, no horizontal asymptote to the right. And if we look at negative infinity, we have to think about which of these things is going to increase more rapidly. 2 times infinity, or e to the negative infinity, which means that negative exponent drops to the denominator and becomes a positive exponent. Well, we've talked multiple times before that an exponential function always increases more rapidly than a polynomial function. Thus, the denominator is going to infinity more quickly than the numerator, which means this is approaching 0, which means that this function ought to have a horizontal asymptote of y equals 0 to the left. So we'll state that this has, along with this x and this y-intercept, a horizontal asymptote of y equals 0 to the left. And that's it. No horizontal asymptote to the right. The next thing that we'll need to do is start taking derivatives. Our first derivative ought to give us the maxima and minima and intervals on which it's increasing, decreasing. So if our original function is f of x equals 2x e to the x, its derivative will have to be found using the product rule. 2x times the derivative of e to the x, which is just e to the x, plus the derivative of 2x, which is 2, times e to the x. We can factor out e to the x from that, leaving us with e to the x times 2x plus 2. And we will set that equal to 0. And we will also think about when it's undefined. We'll do that in a second. First off, e to the x is never going to equal 0 as we said before. But 2x plus 2 will when x is -1. And then we'll note that f prime is never undefined because I can take any number and raise it as a power of e. And I can also evaluate 2x plus 2 for any number and multiply the two numbers together. So we only have one critical value here, that x equals -1. And if we make a sign chart with just -1 on it, plugging in a number to the right of that, like let's say 0, e to the 0 is a positive number. And 2x plus 2 evaluated at x equals 0 is a positive number. Giving us a positive means our function is increasing. Something to the left of the -1 is -1,000,000. E to any power is always a positive value. So that's a positive. But -1,000,000 times 2 is -2,000,000. And if you add that to 2, you're going to get a negative, making this negative, meaning our function decreases. So we'll make a statement that our function is decreasing from -infinity to -1, and not a parenthesis because the College Board wants us to put a bracket in there. And then it is increasing from -1 to infinity. And we will need to figure out what f of -1 is. So we can plot that point. F of -1 is, well, you plug -1 into the original function, you get -2e to the -1, or -2 over e. So it looks like we've got a local min of -2 over e at x equals -1. And it sure looks like that's going to be an absolute minimum as well, right? Because our function decreases until we get down to x equals -1, and then it increases after. So it's absolute and local. And it has no absolute or local max. I'll write that. You should always indicate it doesn't have one. And now we need to plot that point. Well, e is about 2.71828828 something, 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 something. It's a nice little irrational number, or this constant. But 2 over 2.7, you could kind of ballpark that. It's, it's going to be, looks like a little more than 2/3, but probably a little less than 3/4. We'll just kind of throw that point in there at -1. So we'll call this -1. And this is 1, and we'll say that point's going to be right around. Yeah. I think that looks pretty good. And then let's go in here and take a second derivative and see if we can figure out about the concavity of this function. So our first derivative ended up being e to the x times 2x plus 2. So we had f of x was 2x e to the x, and f prime of x was e to the x times 2x plus 2. The second derivative we'll again find using the product rule, e to the x times 2x plus 2's derivative plus the derivative of e to the x times 2x plus 2. And if I factor out the e to the x again, we get e to the x times 2x plus 4. Again, f double prime here is never undefined. But it does equal 0. Well, only when 2x plus 4 equals 0, which would be x equals -2. And we'll make a sign chart to see if we have a point of inflection there. If we plug in something more than -2, for example, 0, into our second derivative, e to the 0 is positive, And 2 times 0 plus 4 is positive. So we have a positive value, and we are concave up. If I plug in something less than -2, like -1,000,000, e to the -1,000,000 is still positive, but -2,000,000 plus 4 is negative, and we are concave down on that interval. So we do have a point of inflection at -2, which means we'll need to find f of -2, which appears to just be -4 e to the -2, or -4 over e squared. So we'll state that this is concave down on the interval -infinity to -2, and it's concave up on the interval from -2 to infinity. And we have a singular point of inflection at -2, -4 over e squared, which we'll need to plot. If e is 2.7-ish and you square that, you're going to get something, I don't know, somewhere probably between, I would guess 7 and 9 somewhere. It's clearly going to be less than 9, but probably about 7 or 8, somewhere in that range. If we do -4 divided by that, let's just ballpark it at somewhere around negative. So if we plot -2, -1/2 right on that one there, that's our point of inflection. And if we try to sketch this, we know that it should be decreasing until I hit x equals -1. That's what our sign chart said. But that we are concave down at first, and then concave up after. And that we need to approach our asymptote. So we're going to be concave down, then concave up from -2 to -1. So I made a little switch in concavity there, but I'm still approaching that horizontal asymptote of y equals 0 to the left. And then after x equals -1, I start increasing, and I stay concave up, according to my sign chart, for the remainder of the domain here. And I stay increasing, and I go through my x and y intercept at 0, 0. And that's what our graph ends up looking like. And that's going to be it for today.